In this video, we're computing the total electric field at a point x contributed to by two positive source charges. We're asked to express this electric field in polar form, and it results from two vector contributions of electric field, so we're going to have to get into a full-blown vector addition problem. Let's start out by just looking at the qualitative contributions to the electric field. So I've already drawn a dotted line from the 5 micro-Coulomb charge to the point of interest. So it's easy to tell which way is directly away. And there's the field contribution due to the 5 micro-Coulomb charge. And I'm going to call that E5 vector. Well, my point of interest is closer to the 3.1 micro-Coulomb charge, but that charge is smaller. So we have two competing things going on here. I can't really tell whether or not this field contribution is bigger or smaller than the first. That points directly away from the 3.1 micro-Coulomb charge, and I'll call that E 3.1 vector. So by the end of the problem, we will have vector added these two vectors. You can imagine picking this one up and sticking it on the head of this one, drawing a vector from the tail of the first to the head of the second, and that's the electric field vector E that we're after, and we need to express this in polar form, which means I need a magnitude and a direction. So we've got some geometry and some trig to work out. I have that the separation distance between the charges is 0.85 meters. But to work out the angle of E5, I'm going to have to get this leg, so the distance from the 5 micro-Coulomb charge to that vertical dashed line. That's got to be 0.5 meters, so that those two segments add up to 0.85. Next, if I'm going to get the electric field strength at this point x generated by this charge of 5 micro-Coulombs, I've got to find the distance to that point, and I'll call that R5. Well, that's the hypotenuse of a right triangle. So let us write it down over here. R5 is the square root of 0.5 squared plus 0.3 squared. And that comes out to 0.583 meters. We also need the distance from the 3.1 micro-Coulomb charge to the point of interest. And I'll call that R3.1. Also given by the Pythagorean theorem. So at this point, I can find the magnitude of the two electric field contributions. First, we'll do the magnitude of E5, and that's given by kq over r squared, where k is the Coulomb's law constant. I'm not going to bother with units in the middle of this calculation because this is already complicated enough. My charge is 5 times 10 to the negative 6. That's what micro means. And my distance to the point of interest is 0.583, and I need to square that. And when I run the numbers, I get 1.32 times 10 to the 5th newtons per coulomb. Do a similar calculation for E 3.1. And this one comes out almost the same, 1.31 times 10 to the 5th newtons per coulomb. Again, there are two competing processes here. The point of interest is farther away from the bigger charge. So it looks like we almost perfectly balanced these effects and got close enough to the smaller charge to make it so the two magnitudes are almost identical. Okay, next, I need to vector add these two vectors. I have their magnitudes, but I need their x and y components, and that means I've got to break them down by using their angles. Well, I can see that the angle for the 3.1 is the same there at the top as it is here at the bottom. And I'll go ahead and call that theta 3.1. And that's the angle whose tangent is 0.3 over 0.35. And when I run the numbers on that, I get 40.6 degrees. I also see that this angle at the bottom by the 5 micro-Coulomb charge is the same as this angle up where the electric field is, and I'm going to call that theta 5. That's the angle whose tangent is opposite over adjacent, again, so that's 0.3 over 0.5, and when I run the numbers on that, I get 31.0 degrees. Okay, now I can get into decomposing these two electric field vectors into their components. So I'll start with E5 and say E5x, that's E5 cosine theta 5. That's 1.32 times 10 to the 5th cosine 31.0. That gives me 1.13 times 10 to the 5th newtons per coulomb. Then I can do E5y component. That's E5 sine theta 5. That's 1.32 times 10 to the 5th times the sine of 31.0. And when I run the numbers on this, I get 6.80 times 10 to the 4th newtons per coulomb. Then I get to the components of the other electric field contribution. E3.1x is 1.31 times 10 to the 5th times the cosine of 40.6 degrees. But if I look at the picture, I see that that component is pointing to the left. So we better make sure we end up with a minus sign in our final answer. And this comes out to negative 9.95 times 10 to the 4th newtons per coulomb. Then I get the y component. That's a sine 40.6 degrees. And when I run the numbers on this, I get 8.53 times 10 to the 4th. Okay, finally, we add up the x components to get the total x component. And I'm going to call this EX. Remember, one of those was negative. When I crunch those numbers, I get 1.35 times 10 to the 4th newtons per coulomb. So the net points to the right, but it's rather small compared to the y part. When I add up the y components, I get 1.53 times 10 to the 5th newtons per coulomb. The last step in finding the polar form of this vector is to put these components together in a right triangle. So I have my x component pointing to the right. Now if I compare the size of these two components, the x component is smaller by a factor of 10. That would be hard to capture in the picture, so I've exaggerated its size a little bit. I'm going to end up with a very steep angle, something very close to 90 degrees. All right, and I've got my x component down here. That's 1.35 times 10 to the 4th. My y component, 1.53 times 10 to the 5th. And what I'm going for here is the magnitude E in the direction given by this angle theta. So E is given by the Pythagorean theorem. And it's not going to come out that much different than the y component magnitude itself because it's so much bigger than the x component. And when I run the numbers on this, I get almost the same thing as the y component, just a little bigger, 1.54 times 10 to the 5th newtons per coulomb. And the direction, that angle theta, is the angle whose tangent is 1.53 times 10 to the 5th over 1.35 times 10 to the 4th. And that comes out to 85.0 degrees. In part B, we're asked to compute the electric potential at this point of interest. And there's an important contrast to draw between electric field and electric potential. Potential is a scalar. So I don't have to worry about all this vector stuff when I deal with potentials. I can just look at the contribution to potential from each of these point charges and add together those two potentials to get the total. I'll start with the contribution from the 5 micro-Coulomb charge. Potential is kq over r. And I get 7.71 times 10 to the 4th volts. Then I look at the contribution from the smaller charge. And I get 6.05 times 10 to the 4th volts. All I have to do to find the total is add up those two scalars. And I get 1.38 times 10 to the 5th volts. So this is a good reminder of how enormous a Coulomb is. If I'm in the neighborhood of these 2 micro-Coulomb magnitude charges, the potential there is hundreds of thousands of volts. If you find the physics content on Zach's Lab helpful, click on the Zach's Lab logo on the right to browse playlists and subscribe to the channel. I produce over 100 new videos per month, and subscribing is the easiest way to find new content. Thanks for watching.